Good day. So, as part of the final third topic, we will discuss the um, this chapter now about beams. So, what now? I believe now you already know or learn about beams in your previous subjects, like the strength of materials, aerostatics, now rigid bodies, and from your reinforced concrete subject. So beams, in here we'll discuss beams, those steel beams, because this subject is uh, the design of for steel design. So um, beams, these are the members that support transverse loads that cause flexure or bending. The axial load effect is negligible. Then the beam column with large akong large axial load, meaning mag-engage na siya o beam to column effect. Then commonly used cross-sectional shapes include W shape, the S, and M shapes. Note that the doubly symmetric standard shapes are the most efficient kind of beam. And the channel shapes are sometimes used, as are beams built up from plates, the eye or box shape. So, ang channel shapes, as you remember, this is shaped like C, no? You can like build this one or built up shapes. Imo siyang isumpay duha, mahimo siya og box shapes or eye shape. So, then magamit din siya for beams. The figure shows in the right shows the height of the shape, no, beam, and the width, no, of the web. And you have this welded part here. So these are also another, no, kind of this one is built up section made from plates. The second figure. The coverage for beams includes the design of members for flexure. This is from AISC specification chapter F, and the design for shear is from AISC specification chapter 7. So we'll discuss this one, no, as this semester goes on. The design for strength, load, and resistance factor design for flexure, the required and available strength are moments. Thus, the NECP equation 502.3-1 or the AISC equation B3-1, that is the ultimate R sub U. This is the factored loads, no? Should be less than or equal to the resistance factor times the nominal loads. Can also be written as, in terms of moment, you have the required moment strength, or from the ACE 7 load combination, should be less than or equal to the resistance factor for bending times the nominal moment strength. For moment, your resistance factor for bending should be, or for flexure, is equal to 0.9. Then this term, no, the resistance factor times the nominal moment is the design strength or the design moment. So this M sub U, these are the moment caused by the load combination. No, this should not exceed, no, the design strength or the design moment. For the ASD, no, actually the same concept naman siya as previous, no, in terms of stress and load. If you remember, for moment, actually, the same concept na siya. But, kini siya, this time, moment lang atong gamit. But, if you remember, this term or this basic concept is actually the same in terms of load and stress. For allowable stress strength design, no, for ASD in ECP equation 502.3-2 or AIS equation V3-2, that is the applied loads, no, for ASD should be less than or equal to the nominal strength or load divided by the factor of safety. Can be written as in terms of moment, um, can be written as required moment strength or M sub A should not exceed the nominal moment strength divided by the safety factor for bending, which is equal to 1.67. If you remember this factor, 1.67, this is the same factor as before, no, in terms of strength and stress and load. Using the factor of safety or safety factor 1.67, the equation above can also be written as equal to 0.6 times the nominal moment strength. The equation for allowable stress design can be determined by dividing both sides of the equation by the elastic section modulus S. No, S, we will discuss this one later. No, how we will define S now later. So dividing both sides by S or the section modulus, elastic section modulus. So this equation M sub A divided by S is less than or equal to 0.6 times the nominal moment over S can also be written as the stress. No, the small f sub b should not exceed the greater. The bigger f sub b. What is this f sub b? No, f sub b is the maximum computed bending stress. That is the smaller f, and the bigger f sub b is the allowable, no, bending stress. So this small f sub b, this is the result of the loads, no, or the applied loads. Well, this f sub b, this is the allowable bending stress. For bending stress, no, for steel, actually this steel is the same concept with reinforced concrete, no. I believe, no, you have discussed or you learned the bending stress in concrete, but the concept actually is the same in steel. Consider the beam oriented in such a way that the bending is about the major principal axis. For an I shape, no, the major principal axis for this shape is this x dash x axis. For linear elastic material and small deformations, the distribution of bending stress is also known. Now, stress is assumed to be uniform across the width of the beam, especially below the yielding point, no, yield stress. The stress is assumed to be uniform across the width of the beam. For example, this one, now we have this simply supported beam with uniform load and concentrated load. So if you try to get the moment or the bending stress, no, the cross section is can be drawn this in this shape, no, I shape. Then we try to draw the bending stress. The bending stress is uniform, no. This one, this upper, no, taas sa neutral axis, this is actually in compression. And below the neutral axis is in tension. Now, if you remember sa inyong reinforced concrete, actually, the same nagyapon. So, above the neutral axis is in compression, represented by this direction of the arrows, and the below no neutral axis is in tension. So, this is the bending stress caused by the applied loads. No, the bending stress, actually this one is the basic concept of your strength of materials. No, I believe na kaagi naman for elementary mechanics of materials, the stress at any point using the flexure formula is written as this one. No, this F sub B, which is the maximum computed bending stress, is equal to the moment times y. This is the perpendicular distance from the neutral plane to the point of interest. No, so kaning y is maximum when the stress is maximum. So if you try to look at the cross section of the steel, no, of the shape, actually the maximum stress, no, is the outermost distance, no, from the neutral axis. Ang pinakadakog stress actually ana is katong pinaka outermost na part, no, sa shape or sa member. And I sub x is the moment of inertia. So this bending stress can also be written as, if you try to get the maximum bending stress, your C should be maximum, or C is the perpendicular distance from the neutral axis to the extreme fiber. If the neutral axis is an axis of symmetry, the maximum compressive stress and maximum tensile stress will be equal in magnitude. No, for especially nga ang imong kuan is symmetrical, ang imong shape is symmetrical. For example, the I shape na or wide flange, symmetrical ang cross section. So the neutral axis is actually at the center, no? So your compressive strength, stress, maximum compressive stress and tensile stress is actually equal ra siya in magnitude, because the distance from the neutral axis to the extreme fiber is the same for both compression and tension side of the cross section. This maximum stress, no, which occurs at the y max or at C, as I've said, is MC, can also be written as MC over I. But this I over C is also equal to the elastic section modulus, or S. So that's why this maximum stress can also be written as M over S of X. No? Now where C is the perpendicular distance from the neutral axis to the extreme fiber, and S of X is the elastic section modulus of the cross section. Note, for any cross-sectional shape, the section modulus will be constant. No? For an unsymmetrical section, the S of X will have two values, one for the top extreme fiber and one for the bottom. Values of S of X, or the elastic section modulus for standard road shapes, are tabulated in the dimensions and properties tables in the manual. If you remember sa inyong strength of materials, actually, the values of this S or the elastic section modulus are already tabulated in the table, no, in the dimensions and properties tables. So naa siya for different shape no of the material. Sa note no, ang any cross-sectional shape na symmetrical no, I already said this one earlier. The section modulus is constant. However, for unsymmetrical cross-section, you have two values for S sub x. Dili siya the same because unsymmetrical man siya. No, dili pareha ang distance from the neutral axis to the extreme fiber, no? Sa compression side lahi and sa tension side lahi. So you have two answers or two values. One for the top extreme fiber and one for the bottom fiber. Equations 1 and 2 are valid as long as the loads are small enough that the material remains within its elastic range. So if you remember sa katong behavior of steel, no, katong stress-strain diagram. So within the elastic range, this equation, no, of bending stress is valid as long as mo fall siya within sa elastic range lang. So I hope you like remember the behavior no those katong elastic stress strain diagram sa steel. For structural steel, this means that the stress, the maximum bending stress, must not exceed the yielding stress, no, and that the bending moment must not exceed. So since within the elastic range man siya, so dapat your maximum bending stress dili siya molapas og yielding stress of your steel, no. So the bending moment is equal to the yield stress times the elastic section modulus or S, di ba? Because the bending stress is equal to M over S man, so that your moment is equal to the product of the bending stress times the section modulus. But this bending stress within the elastic range should not exceed the yielding stress, di ba? Yield stress or yield point, no? We have this plastic moment. Kadto siya is the elastic range, no? Beyond the elastic range is the plastic range or plastic moment. So a simply supported beam with a concentrated load at midspan is shown at successive stages of loading. Now we have this figure. Once yielding begins, the distribution of stress on the cross-section will no longer be linear, and yielding will progress from the extreme fiber toward the neutral axis. So you have this figure, no? Concentrated load, simply supported beam with concentrated load at midspan, no? At successive stages of loading. So meaning, pag-amay siya load hangtod nga moabot ang iyahang mo-exceed siya sa elastic point, so ma-plastic na siya, no? So as you can see here, for the concentrated load, you have this moment, no? And moabot sa point nga like at the beginning of the loading stage, no? Your stress or the bending stress is less than the yield point or yielding stress, diba? Yield stress. So the diagram, no, is actually linear, no? Kung inyong tan-awon diri. Then as as loading progress, so there comes a point nga your bending stress will be equal to the yield stress. So still linear gyapon siya. But after that, no, kung beyond na siya sa yield stress or yield point, dili na siya linear as kani inyo makita diri, no? So ang stress, no, mo go beyond siya sa from the extreme fiber, which is the critical part, mo go beyond siya sa cross section hangtod moabot siya sa neutral axis. Then the member is in the plastic moment na siya, no, after the yield stress or yield point. The beam is in the plastic range, or the beam will encounter plastic movement. So maabot sa point nga naa kay gitawag nga plastic hinge diri dapit, no, sa center. So mura siya na plastic hinge na siya, maabot ang time nga plastic hinge. So plastic hinge, the additional moment required to bring the beam from stage B to stage D, no, is 10 to 20% of the yield moment M sub y for W shapes. When stage D has been reached, any further increase in load will cause collapse since all elements of the cross section have reached the yield plateau of the stress strain curve and unrestricted plastic flow will occur. A plastic hinge is said to have formed at the center of the beam, and this hinge along the actual hinges at the ends of the beam constitute an unstable mechanism. During plastic collapse, the mechanism motion is as shown. So, no? So this is the discussion of the above figures.